Hello everyone, this is Dr. G. Karthik Reddy working as Associate Professor in the Department of EC, MLR Institute of Technology, Hyderabad. And today's session topic is power density spectrum. Okay, the same power density spectrum, or we can also call power spectral density. Power spectral density. Power spectral density. Or in short form, we can call this as PSD. In short form, we can call this as PSD. In this session, we are going to discuss about introduction to power spectral density, relationship between average power and power spectral density. Okay, power spectral density. Before discussing about power spectral density, here spectrum. Spectrum means some range of frequencies. Okay, range of frequencies. This topic comes under spectral process, in stochastic topic. In stochastic topic, spectral process, this is a concept we are having. Power density spectrum, density. Density we are discussing per unit area, mass per unit area. That is a standard definition. Power. Power means we are calculating in a spectrum, per unit area. Per unit area, what is the reflection? Now this power spectral density, PSD, is very crucial. The most application where we are using this is in signal processing we are using, in communication we are using, in spectral analysis we are using. It provides insights into how the power of a signal is distributed over different frequency components. How the power of a signal is distributed. Power of the signal is distributed. This is important. Across different frequency components, how the power is distributed is able to calculate by using this mathematical tool, that is power spectral density. Here we are having, for first example, understand the PSD of a signal. It may be either signal or a process, signal or a process or a function. Here we are calculating for any process or a signal. X of t may be the signal or a process. Find the PSD. It is denoted by power spectral density. Power spectral density we are calculating for the same signal. Same signal. That is why it is denoted by spectral S. S denotes the power spectral density notation. S xx of omega. Xx stands for same signal we are calculating. Next, omega represents in terms of frequency. Omega is the angular frequency. Omega, you know the formula, omega is equal to 2 pi f. Now next we are going to calculate, but this is the definition. Autocorrelation function and the power spectral density form a Fourier transform pair. Autocorrelation function and power spectral density form a Fourier transform pair. Here this is a power spectral density notation. Power spectral density notation. This is a autocorrelation function notation. Generally we are having the definition S xx of omega is equal to integral minus infinity r xx of tau e power minus j omega tau. This is a basic definition. But in place of omega you are having f. This is the formula for power spectral density in terms of autocorrelation function. Now next we are having one more definition, that is alternatively you are having the square of the magnitude of the signal's Fourier transform if the signal is stationary and ergodic. This is also one of the definition of the power spectral density. And one more definition you are having. We are having S xx of omega is equal to time average. With the same thing, same definition, we are elaborating it. Expectation of x square of t by. This is a definition of power spectral density. Second form of the definition. Now next These concepts comes from the basic fundamental concepts of Fourier series and Fourier transform. Okay, before discussing, okay, any periodic signal or any random signal, okay, all are discussed in terms of time domain. But time domain, okay, it is difficult to understand the analysis. So that's why we are converting time domain to frequency domain. Okay, time domain to frequency domain we can because any random signal, okay, random signal, random signal is not satisfied by the Dirichlet condition. The Fourier series and transform is following the Dirichlet condition. The Dirichlet condition is applicable only for the, okay, periodic signals, okay, and aperiodic signals with finite time and finite interval. But here we are discussing about the random signals which are not having any periodic and which is having the infinite time duration. That is why we are going for power spectral density. That is why we are converting the time domain to frequency domain with the help of power spectral density. Okay, the time domain we are taking the in terms of whatever the random signal, okay, random signal x of t. First, whatever you are having, first you are converting in terms of autocorrelation function. Then, by using Fourier transform, we are converting into power spectral density. Then we are calculating the analysis of that particular signal. Okay, this is a fundamentals. You know it already. The Fourier transform x of t. This is a inverse Fourier transform. Okay, Fourier transform. This is a Fourier transform. Okay, and this is a inverse Fourier transform of any signal. X of omega equal to integral minus infinity infinity x of t e power minus j omega t dt. X of t equal to 1 by 2 pi integral minus infinity infinity x of omega e power j omega d omega. This is for the omega interval from minus infinity infinity. This is t interval from minus infinity infinity. These are the fundamentals to understand the concept of power spectral density. Now, okay, this is a important definition of power spectral density. Now we are going to discuss about the average power, the relationship between average power and the power spectral density. Okay, first to calculate that, first you have to assume that, let us assume that, okay, this is any random signal. To understand this signal behavior, first we are considering, we are splitting to certain interval from minus t to t. This is x of t, which is divided to x of t. Okay, we consider this as xt of t. Xt of t equal to x of t for the interval minus t to t. Okay, xt of t equal to x of t only for the interval of minus t to t. Okay, minus t to t, 0 otherwise. Okay, 0 otherwise. Now next, you know the concept of, okay, here integral, assume that minus t to t, whatever we have assumed, t to x of t, okay, this is a random signal minus t to t, okay, minus t to t for all finite t. Okay, for all finite t, we are considering absolute value. This is absolute value of this part is always fine. This condition represents that minus t to t interval xt of t dt is always finite. Now next, we know the condition of Parseval's theorem. Okay, Parseval's theorem. From the definition of Parseval's theorem, it gives a relationship between energy signal in time domain and frequency domain. Okay, this is a xt of omega. Okay, first we will discuss, before discussing the Parseval's theorem. Okay, first this is a Parseval's theorem. Energy, okay, energy in terms of t, integration minus infinity infinity xt of t whole square dt. Okay, then it is equal to 1 by 2 pi integral minus infinity infinity modulus of xt of omega whole square d omega. This is the definition or of Parseval's theorem. It gives a relationship between energy in time domain and energy in frequency domain. Now next, to understand this concept, you have to first to apply the Fourier transform. Previous slide we have discussed the Fourier transform. x of omega is equal to integral minus infinity to infinity x of t e power minus j omega t dt. Okay, you apply it. Okay, now here we are discussing only for certain time period, that is minus t to t. Minus t to t xt of omega integral minus infinity to infinity xt of omega e power minus j omega t dt, which is equal to, okay, xt of t is equal to x of t for the interval minus t to t. Change the interval minus t to t, x of t e power minus j omega t dt. You know this relation, we converted, this is in time domain, we have to convert in frequency domain by using equation 2 relation. Now after substituting that, okay, this is the average power, okay, area under the curve by base, okay, area under the curve by base, okay, power, energy is equal, okay, power is equal to energy by time. Power is equal to, what is the power basic definition? Power is equal to energy by time duration. Total time duration is t minus of t, that is 2t. Then 1 by 2t integral minus t to t x of t whole square dt. Now you substitute that same thing in terms of frequency domain also. Then you are going to get 1 by 2 pi minus infinity to infinity xt of omega whole square by 2t into d omega. If xt of t equal to x of t, okay, x of t, take expectation, here t tends to infinity, we are considering that t tends to infinity. Now because here we considered up to minus t to t in the beginning, but the random signal is having up to infinity time duration, then substitute limit t tends to infinity, then limit t tends to infinity, apply expectation, okay, apply limit on both sides, limit t tends to infinity 1 by 2t minus t to t expectation of x of t whole square dt. Okay, now 1 by 2t integral minus t to t limit t tends to infinity expectation of mod xt of omega whole square by 2t into d omega. And this is the definition of what? This is the definition of time average. Okay, that is why it is represented with a notation. Okay, next. Okay, this is the average power. Okay, average power, this is just a power. Okay, now we are taking for average power because we are taking up to t tends to infinity. Now what you are going to get? Pxx represents average power notation. A is the time average, expectation of x square of t, okay, x square of t. This is a time average of time average is equal to average power. Okay, next, which is equal to, you substitute here, this part is that only in terms of frequency domain, which is Sxx of omega. This is another definition of power spectral density. What is that? Limit t tends to infinity expectation of mod xt of omega whole square by 2t. Okay, expectation of this is called power spectral density. First definition is based on Fourier transform pair. Whenever you are having the autocorrelation function, okay, you can calculate that. That is, we have discussed the first definition, integral minus infinity to infinity rxx of tau e power minus j omega tau d tau. This is the first definition and this is the second definition. And this is a relationship between average power. Pxx represents average power, Sxx of omega represents power spectral density. This is a relationship. Here you can check it that average power is equal to area under the curve of power spectral density. You can observe that area under the curve of power spectral density is called average power. Or we can also tell that, okay, when this one, you can also represent this as rxx of 0 also. Rxx of 0 from the property of autocorrelation function. Means average power is equal to time time average of mean square value or Rxx of 0. We discussed in the beginning, okay, autocorrelation function at Rxx of 0, you will get the average power, okay. And we can also have one more relation, that average power is equal to area under the curve of power spectral density. Area under the curve of power spectral density is called average power. And we also have the definition of the power spectral density, that limit t tends to infinity, expectation of mod of xt of omega whole square by 2t. Okay, this is one of the important definition of power spectral density. Okay, in this lecture we discuss the definition of power spectral density. Okay, power spectral density, that is one of the definition is power spectral density and autocorrelation form a Fourier transform pair. Next, we have discussed the power spectral density definition, limit tau tends to infinity, expectation of x of t plus tau, expectation, this term 1 by 2t, this is the second definition. Now we also discussed that the relationship between average power and power spectral density. Thank you.